Leakage currents in short channel MOSFETs are another source of concern in modern digital design. Leakage currents refer to current flows that are not associated with useful or work-related switching, that is, switching that's associated with computation of logic, but they are background flows of currents due to non-idealities in the device. And in short channel devices, because of the reduced voltage swings, the requirement to reduce the threshold voltage to accommodate smaller voltage swings due to drops in VG and VDS from 5 volts to about 1.1 volts. The lower threshold voltage, VTH, that is frequently designed for these devices causes significantly higher quantity of current that it leaks. Now, there are three major mechanisms through which current leaks in a MOSFET. The principal effect is due to subthreshold leakage, that is the leakage of current from drain to source. Okay. There is a second source of leakage from the gate to substrate, and this leakage comes from tunneling of currents through the oxide layer, from the gate through the oxide layer. The third source comes from junction leakage, that is from the N plus of the drain to the bulk, and this actually arises from the reverse bias diode currents that are leaking, and the reverse bias diode is formed between this N region and the bulk region of the MOSFET. So in this video we will be focusing on modeling only the leakage current that arises from subthreshold conduction, that is conduction from the drain to source without a proper formation of a conducting channel, that is for gate voltages between 0 to VTH. Now an N MOSFET comprises of a N region as the source, a P region in the bulk, and another N region in the drain. And this NPN region also functions, looks and acts like a bipolar junction transistor, where the bulk is actually the base, the drain is the collector, and the source is the emitter. We know that current can flow through from the collector through to the source by modulation of the base, and this relationship is given by I equals IS, where the IS is some small current. This is typically the can be measured by the reverse biasing VBE, and the current is actually exponentially related to the VBE voltage across the base to emitter, divided by KT over Q. Okay, so similarly here in the NPN transistor, we can model the subthreshold leakage current by mapping VBE as the voltage from source from the bulk to source. Okay, and the voltage from the bulk to source is none other than a capacitively divided voltage from the gate, capacitively divided to the source. And so VBS is actually equals to VGS with the capacitive divider, the oxide capacitance plus the junction capacitance at the source. And the junction capacitance at the source, as we'll see in a later lecture, arises from the reverse bias PN junction here in the source. Okay, so this voltage divider term is actually captured in the N parameter here, where N is typically between 1 to 2, and of course VGS here refers to this portion here. gate to source voltage minus the threshold voltage. Okay, and in this equation we see two additional terms. That is the term arising, this eta term arising from drain-induced changes to the threshold voltage. So VTH in transistors in general is not a constant. It varies with temperature. VTH changes with temperature. Increasing temperatures will result in a reduction in VTH, a linear reduction in VTH. VTH is also related to L, the length of the channel. So with a shorter channel, VTH actually increases. So this is why the leakage currents are more pronounced in short channel devices. And there is an effect called the drain-induced barrier lowering, where high voltages, high E fields in the drain here induce a reduction in VTH as well. Okay, and so the effect of Dibble, drain-induced barrier lowering, is captured by this eta parameter here. And we have one more effect to be described, that is, if we bias the substrate, and this is known as the body bias, we can modify the effective threshold voltage, and this is captured by this term over here. And leakage current exists only if there is a net voltage drop between source to drain, because there needs to be some electric field to drive the current in this direction. And if there is no VDS, then there is no non-zero VDS, then there is no leakage current. So the effect of VDS on the leakage current is therefore captured in this term right here. And so rewriting the clean equation, we see our model for the subthreshold leakage current now, which is dependent on VGS, the capacitive voltage divider given by N, the threshold voltage, the effect of Dibble, the drain-induced barrier lowering, given by eta, and the effect of the body bias given by this K gamma. And if we were to take the log of this term, okay, we will see that this section here simply becomes linear, a linear portion, okay, and Vt is actually Kt over Q, the thermodynamic voltage, and the slope is therefore some factor of Kt over Q. The slope of this linear curve, once we take the ln, that is the ln of the current, the log of the current here, versus linear Vg, we will see that the slope will be n Kt over Q, reminding again that n comes from the capacitive divider, and this is given here. And in general, MOSFETs have a subthreshold slope called S. That S is actually arises from this nkt over Q, or between 90 to 100 millivolts per decade. And this means that in order to reduce the subthreshold leakage current by a factor of 10, about 90 to 100 millivolts needs to be reduced at the gate. So a reduction of 90 or 100 millivolts at the gate would result in a tenfold reduction in subthreshold leakage current. And if you watch the video on FinFETs, which are a popular next generation alternative transistors, FinFETs are anticipated to be more efficient devices, efficient in the sense of having less leakage current, because the subthreshold slope for FinFETs are in the regime of 60 millivolts per decade, and so the subthreshold current drops more rapidly with small changes in Vg. And finally, I like to highlight two other important factors in in non-ideal factors, that is the effect of temperature and geometry on short channel transistor behavior. So mobility of the free carriers is also dependent on temperature. As temperature increases, mobility actually decreases, because the increase in temperature causes a greater amount of phonon scattering, which then further reduces the mobility of free carriers in a semiconductor device. And as we've explained briefly just now, the threshold voltage also changes with temperature, but it has a negative linear behavior with temperature, meaning that when temperature goes up, the threshold voltage reduces. And the net effect of this is the saturation current, ID set, would actually decrease with increases in temperature. Okay, but the leakage current would actually increase with increases in temperature. And now to talk about the geometrical issues of transistors, because we have very small dimensions of width and length in transistors today, the precision at which we can fabricate these lengths and widths precisely is not that great. So if we were to say specify a transistor to be 5W and another transistor to be 3W, the ratio of these transistors may not exactly end up as 5 to 3. And so what is frequently done, transistors are constructed to some unit ratio of width to length, and if a 5W transistor is required, what we end up doing is connecting in parallel 5 of these unit transistors as such. And this way we get a dependable and a robust ratio and a robust way to scale width, length, and various parameters in the transistor.